global warming real? Is climate change irreversible? Why are carbon emissions still rising? Join host Dr. Alberto Troccoli, a global leader in climate science and its application to the energy sector, as he unpacks these pressing issues. Through candid conversations with leading experts, get ready to demystify climate change and explore its many layers. So, let's communicate!
Hello, I'm Alberto Troccoli, and welcome to the Let's Communicate podcast. In this episode, our guest is Professor Steve Koonin from the Hoover Institution at Stanford University. I hope you enjoy our conversation. Hello, Steve. It's a pleasure to have you at our podcast, Let's Communicate. Welcome.
Good. Happy to be talking with you.
Thank you. So I'm really impressed about your bio. I mean, you've done so much from Caltech to New York University to BP and none others than undersecretary under the Obama administration, didn't you?
For 2.5 years, I was the Undersecretary for Science in the Department of Energy.
Yeah, that's impressive. I'd just like to hear maybe your experience at Caltech, because I know you also met Richard Feynman when you were there, no?
Yeah, so I was first at Caltech as an undergraduate. I grew up in New York, but at age 16, traveled across the country to study at Caltech. Dick Feynman, and particularly the Red Books, the famous Red Books that he helped put together, were an important reason for going to Caltech. It was the hardest university for science and engineering, and I wanted to challenge myself.
Yeah, that's probably one of the few things not few things, but we have that in common. I when I saw and read that you were attracted by the Red Books by Feynman, that attracted my attention, because that's what I used during my studies in physics. So that was really good.
So I can tell you briefly an interesting Feynman anecdote. After I finished at Caltech as an undergrad, I was more or less sent to MIT to do my PhD in nuclear physics, with the understanding that if things went well, I would come back as a junior faculty member. And so in my third year at MIT, I was finishing up my PhD, and I came back to Caltech to do my hiring talk, if you like. And it was the big weekly physics colloquium with a couple hundred people in the audience that I had often attended as an undergrad, sitting way up in the back with the old guys in the front, Feynman among them. And so I started in on my talk, kind of nervous because Dick, among other distinguished physicists, is sitting there in the front row. About 10 minutes into it, Feynman says, "I don't understand that. Please repeat." And I did, thought I explained it. 10 minutes later, he pipes up and says, "That's got to be wrong. I can't understand that." And I thought, oh my God, I'm finished. I get through the talk finally, and as the audience is breaking up, Feynman bounds out of his seat and says, "You did fine. I was just testing you." And, that's kind of the way he was. Just wonderful person, as well as, of course, an amazing physicist.
Yeah, fantastic. Very nice, very nice. So yeah, like you also have a degree in physics, and but then I moved to oceanography, and I just take the opportunity also to introduce briefly our podcast. It's a new podcast. It's called Let's Communicate, and it's really a way to bring together people from all spectrum of the debate on climate change. My purpose is really to try to connect or reconnect the people, because as we know, there is quite a lot of polarization in the debate. I'm keen to see whether we can find some common ground. So I'm inviting people from all parts of the spectrum, like from one end where people think that climate change is not nothing to worry about, to the other end where the world is going to end now. So we have this broad range, and I'm really keen to see and hear from all people that are part of the debate, and see whether we can really reconnect. Having said that, I would like to just start with some general questions about climate. Also in reference to your book, of course, Unsettled.
Mhm.
I should say that I haven't read it all. I've read it, parts of it,
Okay.
but yeah, sorry, lack of time. But
No, that's fine. By the way, I hope if you've read it, you've read the updated edition, which came out in June of
well, unfortunately
2024.
Unfortunately not.
Yeah.
But anyway, so let's start with the first question. I'd just like to, just a very broad question about the gaps, how you see the gaps and uncertainties, as well as the things that we know about the climate. I mean, how do you see the situation from a broad sense in terms of climate change?
Yeah. So I think the science questions are, first of all, how has the climate changed in the recent and distant past? That's an observational question. The second is, how is the climate going to change under natural and growing human influences? And the third is, what will be the impact of those changes on ecosystems and on society? Of course, the big question, which I hope we'll get into, is what should society do about all of that? The science questions are really observational, modeling, and then the higher level ecosystem societal impacts. If I start with the observational side, I think what we're missing are long, detailed observations to quantify the natural variability. One of the things I like to point to is, as you probably know, there's almost 1,000-year record of the height of the Nile River as measured in Cairo. And that's a pretty interesting climate proxy because it drains about a third of Africa and quantifies the natural variability of the hydroclimate. And when you look at that, apart from large year-to-year variability, what you see is century-scale trends in the height of the Nile. And so, for example, from the mid-7th century to the mid-8th century, it was going down a lot when you look at the average. And that's a natural variability. And you have to understand that kind of natural variability before you can say, aha, it's CO2 in the modern record. So I think that's one. The second is we need better understanding observations of the oceans. The oceans are the long-term component of the climate system. They absorb most of the additional heat that's coming into the planet. And we have pretty poor long-term observations of the ocean, particularly at depth. That's starting to get better as we deploy floats and have other technologies to understand what's going on in the deep ocean. But it's got timescales of up to 1,000 years. And unless you understand that, again, it's kind of tough to say that's CO2. So that's on the observational side. Of course, the projections rely on models, very big computer models. You probably know them as well as I do. But from the point of view of other modeling that one does in science and engineering, the models are in a pretty poor state. They don't get the temperature, the equilibrium temperature of the Earth right to within a couple degrees. They need to be adjusted or renormalized. We have a pretty poor understanding of the feedbacks in the models, particularly the clouds are problematic. The resolution is a problem. The current state of the art, as you know, is probably about 100 kilometers on a side. And it's very difficult in terms of computer power to get down to resolutions that would be useful, let's say 10 kilometers or so in the atmosphere. So all of those things together say you should take what the models say with a grain of salt. If you look at the equilibrium climate sensitivity, which is a measure of how the climates respond to external influences, it varies by a factor of 2, 3. So we don't know more than, as Tim Palmer says, it's only a fuzzy picture at the global level and not at all fit for purpose at the regional or local levels. So I think those are some of the things we should all be, as scientists, working on, but also communicating clearly to non-scientists about what the certainties and uncertainties are.
That's great. I mean, I'm actually fascinated by you, what you've done, because coming from theoretical physics and learning all these things about the climate, it must have taken quite a lot of time. I know you're a fast learner, but it's
well, you know, two things about that. One is one of my elders, when I just gotten my PhD, said, you know, a degree in theoretical physics is a license to poke your nose into anybody's business. And yes, you know, the physicists, we have the tools, fundamental understanding, mathematics, clear thinking, and so on, to be able to jump into other fields. One does not do that lightly. I mean, I first got exposed to climate science in the early 90s and had the fortune to meet and learn from many of the senior figures in the field at that time in the course of doing studies for the government. But I would say I've been at it seriously for 15 years or so. There's a lot to learn.
Yes.
And one is always learning and surprised.
Of course. Like we know, there's not a single person can understand all the aspects, and so there's so much complexity. But you mentioned many interesting aspects. I'd like to try to unpack some of them. So when we look at the climate record, the first thing we do normally is to look at the global variables. So the global temperature and the global emissions. I mean, it's good to have some records like the Nile and other places. The problem is that there are, even though they cover quite a large space, there are still parts of the picture, and to try to generalize from that sometimes is difficult. What is your view on this?
Look, globally is probably in some ways the least noisy record on multi-decadal scales, and we see, of course, the temperature globally, the global average temperature anomaly, if you want to be precise about it, has gone up by about 1.2, 1.3 degrees since 1900. But on shorter time scales, there are anomalies that we still don't understand fully. As you probably well know, the last couple years have seen a significant spike in the global temperature anomaly. And there's still a lot of debate about what has caused that, and in fact, whether the spike will go down or not again in the next year or so. I think it will. But, you know, causes include the cleaning up of aerosol emissions from marine transport. El Nino is just coming off. A lot of water vapor injected into the stratosphere from subsea volcano a couple of years ago. So, and we don't know. There's still a lot of debate about that. So the fundamental problem is that human influences are a small physical perturbation, 2.5 watts per square meter on a radiation flow that's about 240 watts per square meter. So it's 1%. It's a chaotic system. It's poorly observed. And so it's a grand challenge to try to understand the response to human influences.
It is, yeah. Of course, there are many variables, but the fact that the temperature is increasing, the emissions, particularly CO2, is increasing. I mean, this is quite a strong correlation, and to explain it otherwise is also not easy. So if one is to explain why it's going up, we should also explain why they wouldn't go up. So, for example,
well, I'm sorry. Why the? I missed that word. Why the?
If we are saying we need to understand why they're going up, we would need to also say why they wouldn't go up if, say, greenhouse gas go up. Why temperature wouldn't go up? Yeah. But to your point about the 1%, actually, this is one of the parts that I saw in your book. You made you clarify that point that if you take a 1% in radiative forcing, it's about 1% in temperature. So they actually line up if you want to look at that way. But also, as we know, the CO2 has a disproportionate effect because of the spectrum. I mean, probably we don't want to go into the details, but you know very well, no, that because I also understand listening to your interviews that you are also saying that CO2 is increasing and is driving temperature. So that's something that you give as a fact.
It's of course not the sole. It's not the sole driver. There are other anthropogenic drivers. There are natural drivers. I like to talk about radiative forcing rather than CO2 for that reason, because aerosols are significant at the level of 1 watt uncertainty. But, there are longer-term variabilities we don't understand. For example, the temperature anomaly went down a little bit from 1940 to 1970. It rose just about as much, not quite as much, but as strongly from 1900 to 1940 or so. And then we've got the longer-term warming from the Little Ice Age, from the 17th century. So there are things going on that are of a scale that says, gee, I'd really like to understand those before I say that all of the current warming is due to anthropogenic greenhouse gases.
Yeah, absolutely. I mean, the research is continuing. There's no doubt about that. But for example, are you familiar with the global dimming?
Of course, and I like to say perhaps a project I started was one of the first to have detected that. Back in 1990, 91, we started observing the moon, and particularly the dark part of the moon, to measure the light reflected from the Earth. And a couple of years ago, we published a 20-year record, which showed, in fact, that the Earth was getting somewhat dimmer. The albedo was going down on a climatologically significant scale, worth about a half a watt or maybe 1 watt per square meter over 20 years. I was very pleased when the satellite observations confirmed that. It's a mystery. I think we don't understand that. Of course, some people say, well, the models show that same behavior. But of the several dozen models, you can always find 1 or 2 that show something like that. Yes, global dimming is observed, and I think is largely not understood, but is certainly of a scale significant for understanding the climate.
Okay, but normally when people refer to global dimming, just to add to what you said, it's also referring to the particular period between the 50s and 70s when there was an excessive amount of aerosols, particularly in Asia, and that was linked to the reduction also in temperature and radiative forcing. So some of the explanation.
Yes, although if you look at certainly that was perhaps a factor. But if you put in what you think are the aerosols during that period into the models, you don't get it right. And again, I can't pull up the references as we're talking, but that decrease is not well understood. We know that there are long-term variabilities in the system, and the models will probably not get those right, either in magnitude or in phase. You can't brush that aside as you're trying to understand the global temperature.
In terms of modeling, so you mentioned the modeling. So we know it's a very complex. You need to take into account many processes. You often refer to the climate modeling that has a resolution of 100 kilometers. So each box has 100 by 100 kilometer, which is entirely correct with most of the current projection models. But we also have very accurate models for present day, which give us the confidence that when we look at the future, because they use the same physics, then they can reproduce to some extent with all the uncertainties, of course. How do you see the relationship?
So I would disagree with that a little bit. I mean, weather is a fundamentally different problem than climate, as you well know. But it's more than that. if you take a climate model and you say, it describes the present day climate very well, that is not answering the question that you want to know, which is how does the climate respond? And the response of a system is very different than the equilibrium state. A non-technical example is if you've got a brick hanging on a string, and you might say, okay, I understand the brick, it's just hanging on the string. But that's a very different question than how much would the brick move if I knocked it. That's the response to an external system. Depends on the mass of the brick and so on. So the fact that we can describe the current system well, you might say gives some confidence, but even if we take the ensemble of models that describe the system well, they still give very different responses to the system, to the external influences.
Could you expand a little more when you say different responses? Responses in what sense?
Well, at the global level, just the equilibrium climate sensitivity. If you take the models only and not include the observational constraints that the IPCC uses to fix the problem, they go from 1.5 up to 5 in terms of the temperature rise you would expect if you doubled CO2. That's an enormous range on the scale of things we care about. Certainly, if it were 1.5, it would make the response much less of a concern than it is if it were 5, which would be ringing the alarm bells.
But does it tell you anything, the fact that all the models are, even given the uncertainty and the spread, they're all showing an increase in temperature to different degrees, but there's none of them that is showing a decrease?
Well, I think it's simple physics, and I would teach this in the courses that I taught. If you increase the infrared absorptivity of the atmosphere by adding CO2, it's going to increase the surface temperature of the planet. There's no question about that. That's simple physics. The problem is the feedbacks, one, and the fact that you're, at a 1% perturbation, you're kind of in the mess. And so when you look at how people tune the models, for example, they'll adjust how snow affects the albedo of the boreal forests, right? Who would have thought that matters? But at a 0.5 watt, it does matter. So lots of small details matter at the scale that we're talking about if you want to get quantitative.
So to summarize, in terms of climate modeling for the future, what is your position or understanding of how the situation may evolve, given that we are committed already to an increase in greenhouse gases, and we know the temperature is increasing?
Look, if you want to work to improve the models, which I think we should, it's a massive effort to shrink the resolution. It goes as roughly the third power of the horizontal resolution. And so to get from 100 kilometers down to 10 kilometers is a factor of 1,000 in computing power. Maybe in 30 years we'll get there. I have more optimism about the application of machine learning and artificial intelligence to deal with the subgrid scale parameterizations. There are efforts going on, one centered at Columbia University, there's work at Caltech, other people trying to apply AI to the climate problem, not only perhaps the subgrid scale, but also the general modeling. So maybe something is going to happen there. But people then just need to acknowledge perhaps we'll never get precision sufficient to de-risk our response. We're just going to have to live with the fact that it's going to go up. And it's likely that as we get another decade or two of good observations, we'll get a little bit better sense of what the real sensitivity is.
So in terms of, just to summarize, what is your position and view? So if you were to say what should be a mean temperature from what the results have you seen, the global temperature, what would be in 2050 or 2100, for example?
Yeah, I see no reason to differ from the IPCC estimate for a moderate emission scenario. And by the way, the emission scenarios are moderating as we go on. Something like rise above pre-industrial of 2.6, 2.7 Celsius is probably what we could expect, what we should plan for, of which we've already seen about a half of that, or 1.3 or so. By the way, I'm sure we'll get on in a moment. Maybe this is a nice segue to the issue of societal impacts. We have already seen 1.3 degrees since 1900, and during that time, we have seen the greatest flourishing ever of humanity. Perhaps despite or because of that warming. You look quantitatively, lifespan average has gone from 32 years to 73 years. GDP per capita in constant dollars has gone up by a factor of 7. Literacy rate has gone up to 80% from 20%. And the death rate from extreme weather events has gone down by a factor of 50. All right, even as the globe warmed by 1.3 degrees. So I think that gives one a good sense of optimism that even if we do nothing about increasing greenhouse gases, that we're not going to get significantly derailed. It's not a guarantee, but I would say it might be a necessary condition for optimism.
No, it's good. It's good to hear that you're optimistic about this situation. And what is your view in terms of, you said that in the future we would expect another 1.5 degree or thereabout, maybe a bit less, 1 degree. What reassurances do we have that the future will behave like the past? It's like in finance. Who tells us that, given that that the system is highly nonlinear, as you know, we're already seeing some changes in the Northern Atlantic. We know that there is a very highly nonlinear system that is at play there with the deep water formation. And who can tell us that that's not going to be triggered by even half a degree more?
Yeah, right. You can't. There are no guarantees, but you can try to look at the historical record. You can look at, let's say, the last 30 or 40 years. Every once in a while, there's a paper that says the AMOC is slowing, and the circulation in the North Atlantic is slowing down, and then it turned out to be wrong, and so on. It sticks in my head a quote from Carl Wunsch, whose name I'm sure you know, a very distinguished physical oceanographer. He says that the North Atlantic circulation is an unavoidable consequence of the equator to pole temperature difference and the Coriolis force. The strength is up for grabs, but show me 100 years worth of record, and then we can have a discussion about whether it will or will not slow down. So future is not guaranteed, but you can look at the past, you can look at the models, and try to make some reasonable inferences. And you know what? If it does change, it's going to take decades for that change to set in, and society will have an opportunity to respond as it has responded to other changes in the past.
This is also considering then that we are continuing to emit and we are committing the changes in the climate system due to the increased greenhouse gas. And as you know, the lifetime of you also mentioned it in your interviews and so on, the lifetime is very long. So once the CO2 is in the atmosphere, then it takes a lot of time to get out. So if we look at such a risk of possible slowdown of the circulation, and you might have seen also latest IPCC related work, which says that the boundaries are coming very close to being hit now with some of the tipping points.
Look, I mean, there's a risk, but the response requires a balance. And what I would say is that, we might fret and clutch our pearls at the possibility of some catastrophic change. But the rest of the world, the developing world, has that way down on their priority list. The real crisis for 6 billion people is not having enough energy. And it's a very real, very immediate, existential, and soluble threat for them. Whereas the kind of things we're talking about in the climate, they're far off, they're vague. You can't say, what are you really worried about? I once asked Dan Schrag that in some public discussion, and he couldn't give me an answer, right? So you got to balance all of those things, and the public discussion has not had that element of balance in it.
Okay, so let's move to the societal implications. You already mentioned what happened. You mentioned the what was the decrease in impacts. It's been reduced by 1/5, I think you said.
I'm sorry.
The impacts from severe events.
Oh, the death rate,
the
fatality rate from extreme weather events has gone down by a factor of 50 since 1900, and that's due to better resilience in society, better prediction of storms, for example.
It's good that you acknowledge also the some of the reduction is due to better predictions, which doesn't alleviate the problem that the events are still happening. In fact, statistics, I've seen statistics that show that meteorological events are increasing and damages insured. If you look at the insured losses, I don't know if you looked at some of the statistics, for example, from Munich Re.
I have. I know that. Yeah,
they are around $200-300 billion in the last years and increasing. So how do you square that with that?
Right. Yeah. So first of all, let's talk about the weather events themselves. If you look at Table 12.12 in the IPCC Working Group 1, they list a couple dozen climate impact drivers, as they call them, right? And heat, drought, flood, storms, sea level, and so on. And whether they have seen an emergent trend in those different types of events. And, most of the entries, the majority of them in that table are blank. Okay. Hurricanes or tropical cyclones, droughts, floods, and so on. No. Yes, it's there for temperature rise, for heat waves, but everything else is blank. So when everybody says, extreme events are increasing, I don't understand the disconnect there. That's the first point. The second point is on the economic impact of extreme events. It's easy to talk about big numbers. $300 billion on a global economy of 80 or 100 trillion is a couple tenths of a percent. And if you look at the trend scaled by GDP, or global economic activity, or U.S. economic activity, the losses are at the couple of a percent level. Roger Pilkey keeps track of all of this, and Roger Pilkey Jr. It's a couple tenths of a percent annually for extreme weather losses, and actually going down globally over the last 30 years, not going up slightly.
Okay, so that's the statistics from Munich Re maybe says something different. I mean, the statistics.
Well, actually, Roger's data comes from Munich Re, among other sources. It's easy enough to look at the published stuff.
Of course, yeah. So we'll relate to that, but also on economics, and actually we will have Roger as one of the invited guests in our podcast.
Good.
So we will talk with him as well. I also heard you mention the work of Nordhaus and looking at impacts in the longer term from an economic perspective. And initially he had an estimate of 1 or 2%, which has been now updated and increased, as you know. So if we're looking at maybe 3-4%, which is looking, but this is there are so many estimates, no, of the impact from an climate from an economic perspective. But even then, 3-4%, as you were saying, out of 100 trillion, it's about 3 or 4 trillions a year. So it's not so small. We're always looking at the global level.
So, right. I mean, it's certainly not 3 or 4% currently. It might be, 3 or 4% in the future. We should talk about the estimates in a minute. But even if it is, if the economy is growing at 2% a year, 3 or 4% is only 2 years worth of growth. And so what that means is the economy might be 3 or 4% smaller than it would have been otherwise, but meanwhile it would have gone up by a factor of 4, let's say, by the end of the century. So it's a small effect. The White House, this White House, Biden, put out a report a year or two ago showing it's a few percent for a few degrees, the consensus of a dozen different estimates. Yes, there are estimates that show it could be a lot bigger, but most of those give implausible projections. Bjorn Lomborg has pointed this out. For example, that Mongolia becomes 4 times richer per capita than the US in one of the models. The physical climate modelers have learned to prune the modelers on the basis of plausibility. And they throw out 30-40% of the GCMs because they're deemed too sensitive. In the same way, the economic modelers should be pruning their models as well, and they haven't gotten to that level of sophistication yet.
So, yeah, that's a good point, because you are drawing this parallel between the climate models, the projections we discussed before, with economic models. And you were pointing out that climate models have large uncertainties. So why would we trust an economic model, which we know is much more uncertain? They are not able to even predict what's going to happen next year, never mind 100 years from now. So how confident are we that those numbers are trustworthy?
But, again, there's, first of all, a consensus among the models that give plausible results. The second is the experience we've had that I talked about already, societal development since 1900. And the third, we've also touched on, is the recent, let's say the last 30 years experience as the globe has warmed about what the impacts have been. You can't have absolute certainty, but it's plausible. And again, it's a balance question. Yeah, there's perhaps some threat from CO2, but you've got to weigh that against the other demands that the globe has, particularly for reliable and affordable energy for most people.
So when we look at the costs as well of energy, like you just mentioned, and the fact that we are running this underlying risk of increased costs, even if it was 1 or 2% in 2100, we're still talking a few trillion then. So if we look at the costs of the meeting the targets of net zero, let's say by 2050, I heard you say, I don't know if you have other estimates, more recent estimates, but you were saying that there are no estimates actually about the cost of what it would take to reach the 2050.
No, I wouldn't say that there are no estimates. There are some estimates, and they cluster around 5% of GDP per year over the next 30 years. I think the notion that we're going to hit net zero by 2050 globally is a fantasy. All right, even Al Gore, John Kerry, Jim Hansen, they all say this is not going to happen. And in fact, anybody who studied this, as I did starting 20 years ago, would come to that conclusion just on the basis of techno-economic facts and potential. So let's stop with the notion of net zero by 2050, maybe 2100. We should get real. One of the problems in this climate energy discussion is the lack of a realistic, transparent, and complete portrayal of not only the state of climate science, but what the techno-economic realities are of energy. The fact that reliability and affordability come before greenhouse gas emissions. The fact that energy systems are slow to evolve for various fundamental reasons. And the fact that the world's energy demand is probably going to go up by 50% over the next 30 years as most of the world develops. And laying out those facts is something you see rarely done in the popular or even semi-professional literature. But they are facts, and they condition what we could or should or will do about this issue.
I heard you say also that a lot of the studies that show the net zero or the energy transition in general, increased in renewables and so on, are done by academics only. And so I would like to hear your view about also what the statements made by the International Energy Agency last year about the tripling of renewables by 2030, or other studies. For example, in Australia, we had the first study of 100% renewable as a feasibility more than 10 years ago. And another study from, this was done by the Australian energy market operator, so people in the sector, people who run the grid.
Right.
And similarly in France, they run 60% renewable target. This was done by EDF. So these are people who know what they're talking about when it comes to energy. So it's not just academics.
Right. So when you talk to people in the energy sector, they are daunted, if not horrified, by the need to rapidly decrease emissions. And let me do a simple explanation, which I'm sure you know well. Yes, wind and solar are the cheapest ways of generating electricity. There's no question about that, assuming the lifetime is what people claim it is. But that doesn't make for an electrical grid. An electrical grid has to be reliable. And wind and solar, as you well know, are intermittent. And you can have long periods, if you look at weather statistics, where the wind is becalmed and the sun is not shining because of clouds. Dunkelflauten, to use the German word dark stillness. And the electrical grid has to keep providing electricity during those 2 weeks, 3 weeks, a month in Texas. Rare, but not unprecedented. And so you need some kind of backup, whether it's massive storage or whether it is firm dispatchable power like nuclear or carbon captured gas or coal even, you'll forgive the word, to ride through those Dunkelflauten. And that system needs to be at least as capable as the wind and solar. And so it's going to be at least as expensive. In other words, what you need to pay for is reliability, not generation. Now, when people do studies with real weather statistics and real demand, you discover that the cost of the system is 2 to 3 times as much as just the wind and solar by itself. So, renewables, I like to say it's an ornament, but it can never be the backbone of a reliable grid. So, if you ask me today, what do we do to build the grid? I think it's got to be nuclear power. That is reliable. It's not outrageously expensive. Proven technology and so on. And, you're discovering, for people in the UK and in Germany and New Zealand, They're discovering that already, that you cannot completely rely on wind and solar. You need that backup.
Certainly, you need some backup, although there have been also studies in Germany showing that the Dunkelflaut is not an excessive problem, given the spatial dimension of the country where they can balance wind and solar. There's been recent analysis showing that they can balance very well. But on a more practical level as well, what do you think of countries like Denmark that are pioneers in wind, and they've reached 60% of penetration? There's other countries like Uruguay or Paraguay who are which are very high, nearly 100% renewables. Right.
So, I had the fortune to live in Denmark about 45 years ago for a year or so. So I got it. Not a great manufacturing country, so the demand is not as high as it is in some of the manufacturing countries. But more importantly, they've got this great big cable under the Öresund from Sweden to Denmark, and perhaps cables from Germany to Denmark, that provide the backup for them. It's not the penetration that you should be paying attention to, but how often, rarely, but when you need it, you need it. How often do they have to import? So you're paying for the capital cost of a rarely used but occasionally essential backup capability.
Yeah, the capability of backup is available also. You're probably aware of the cable that is being constructed between Norway and the UK, for example. But more generally, the approach in Europe is really to try to connect as much as possible to balance the grid across countries. And that's a real advantage in the collaboration that there is. And that also overcomes the problems that you mentioned. But
So you need, in the U.S., you need to go to continental scale integration to get to 99%, which is still not enough for a system that's all wind and solar and storage. I have, a paper just came out last month from Ken Caldera, Nate Lewis, and so on. Real weather statistics, real demand. And you need to take 40 years of weather statistics and demand at a continental scale to get the kind of reliability that we demand in a developed country. There are studies, I don't know if they've been done, but there were studies underway in the UK. I helped stimulate them a couple of years ago of the same sort.
Solutions, there are many solutions, of course. We also know that some of the costs are going down dramatically also in terms of electrical storage. There is a lot of research and they are projected to decrease a lot. The solar is also going to decrease a lot. But I would like to switch to another topic. But before we do that, I'd just like to have your comment on something that is not very well known and not very well discussed normally. You would be aware that there are some strong subsidies for the fossil fuel industry. They estimates run at 7 trillion a year compared to 1 trillion for renewables. And if you consider that the 7 trillions might have run for the period that fossil fuel have been around, let's say 70 years or so, we could run at the scale of around 500 trillion over the period, just as a rough estimate. So what would be your comments on?
Yeah. So you might ask, why do fossil fuels get subsidized globally? I mean, we can turn to the U.S. numbers in a minute, which I know somewhat better. And it's because governments in poor countries need to keep energy reasonably affordable for people. Otherwise, you have revolutions and changes in government and so on. In the U.S., the situation is quite reversed. The subsidies for fossil fuels are a fraction of what the subsidies are for alternative energy sources, technologies, and even more disproportionate if you scale them by the amount of energy actually produced. I would be in favor of taking off all subsidies on everything. All right, let the markets decide. Unfortunately, the governments can't resist in weighing in. And look, you see things do not go well. Look, the UK has got real energy problems. Germany is a basket case because of their attempt to intervene in the energy system. You know, people ask me sometimes if they're in governments, what should we be doing? And what I say is, look at what Germany has done and do the exact opposite. All right. I would not want to be living in Germany at the moment.
Well, I mean, Germany actually also allowed the transition to using solar energy with the investments they did more than 10 years ago. That then it was obviously taken from them by the Chinese. But if Germany hadn't spearheaded that effort, they wouldn't be there. And of course, one would expect also some bumps on the road, and the war in Ukraine was not expected. And so that's also why
I was happening even before the war in Ukraine. And look, the UK is in the same boat. Look at the electricity prices in the UK and the subsidies that the government has and will have to lay out in order to pursue this absurd goal of offshore wind. All right. I mean, the people who make these rules and set these policies have no sense of the scale of the reliability of the difficulties in producing a useful energy system. Right? And I think it's part of the responsibility for people like you and me and others to lay out clearly what the consequences are of various policies. And we have failed to do that.
Of course, yeah, there is a question of reliability. There's also, how much reliability you are able to and want to accept, because obviously you can change the level of reliability. And there's a question of cost. But ultimately, I think it's also about which world we want to live in, how we imagine, energy to be generated, and what are the consequences for each of the energy source. So there are more considerations.
And most of the world wants to live in the world that we in the developed world live in, right? The 1.5 billion of us in the EU, in the US, Australia, Japan, and so on. And to have that kind of lifestyle takes energy.
Of course, but they are doing, and also they are with the help of China, for example. There is just recently, there is in Tanzania, they built a huge hydropower plant of more than 1 gigawatt. So, that's going to provide huge benefit to the people there in Tanzania. And they're doing something similar in Malawi, one of the poorest countries in the world. And so, there are ways to leapfrog also development compared to what we've done.
Hydropower is great when you've got the geography that lets you do it. The world is kind of tapped out on large dams globally, and forbidding those folks, as the World Bank does, from building fossil plants, I think is immoral. You're not letting them have the energy that they need. And even if the West says we're not going to fund a coal plant, China's going to come in and do it anyway. The world gets about 80%, maybe 81, 82% of its energy from fossil fuels. That's been the case for the last many decades and will likely continue to be the case as the world, most of the world, satisfies its existential need for more energy.
That may well be the case.
No matter how much we might wish that they reduce their emissions, their first priority is just getting energy.
Of course, they need energy, but like I mentioned, in the case of Tanzania and Malawi, going with a hydropower generation that will decrease, and many of those countries are also looking at options of renewables. So it's not necessary to go through the same path of the developed world. There's
if we in the developed world are willing to help and pay for it, yeah, okay, but cash is not abundant in Europe or in the US. these days. So, the world has spent, I don't know how many trillion, about 10 trillion roughly over the last decade on renewables, and we're still at 82% fossil fuels. So the renewables will very likely be an add-on to other forms of energy, as opposed to a displacement. And that's what's happened historically. And again, there are fundamental techno-economic reasons why that's been the case.
Okay, I would like to switch now for a few final questions around what you state in your book and your book in more generally. So the fact that how we try to balance uncertainty and action, and also, reminding the title of your book, Unsettled. And so in your book also you mentioned that you may have inadvertently broken some code of silence, and like mafia's omerta. Could you elaborate on what you meant by that, and how you believe your perspective fits into the broader climate science perspective?
Yeah, if you sit down and have a discussion about climate science with researchers active in the field, I don't think you would find much disagreement between what I've said in the book and what people would agree to. And, I've had comments recently from Kerry Emanuel at MIT, from Dan Schrag, who would say, yeah, Steve, I agree with most of what you have written. Where the silence comes in is how some of that, the science, is represented to the public. And, an example I like, which is if you look at the summary of AR6, the high-level synthesis, there's a line there that says, extreme heat has contributed to increased fatalities. And that's all it says about fatalities due to extreme temperatures. What they have left out, and you can find in the research literature, is that the decline in extreme cold associated with warming has actually reduced fatalities much more than the extreme heat has increased the fatalities. And so, as one of my friends like to say, that statement in the IPCC report is completely factual, but factually incomplete. And it is the complete picture that is absent from public discussions, whether in the media or the politicians or some of the scientific societies. And I think it is the responsibility of those of us who have a more complete understanding to paint that whole picture and then let the public debate happen.
So the policy summary normally is obviously needs to be selective, because you cannot fit all the information that is in the full report. So I was just wondering whether you are you saying that the fact that the deaths are diminishing for cold is a good thing, so we should allow the climate to warm even further so we can reduce that further?
Well, I think we need to paint a complete picture of what the impacts of the changing climate are. And there are some benefits. We talked about just now the decline in cold-related deaths. Crop yields have gone through the roof over the last 50 years. And again, according to NASA and the IPCC, a lot of that improvement in yields is associated with increased CO2 levels. So we need to paint the complete picture that there are benefits and disbenefits and societal impacts, both positive and negative, that we need to lay out for the public and not just paint a one-sided picture, which is what the IPCC does.
Although, as you also said, the reference to that statistic is available in the report and the full report. But we also do
But who reads the back of the report, right? You need to be a scientist to be able to do that.
But the other fact is also that you'll be aware that there is an asymmetry between the heat death and the cold death. The heat death is more sudden. It occurs over a shorter time frame, so it's actually less controllable from a heart condition point of view than a cold one. So having control over the heat effect on cardiovascular issues, although I'm not a physician, of course, it's something that needs to be taken into account because of the severity of the effect, more so than with the cold.
Okay, I don't know about that. I try not to talk about things I don't know about. But if you just look at the statistics as published in The Lancet, for example, there are 9 or 10 times as many people die from cold than from heat globally.
Yes.
And most of those deaths, I believe, are in Asia. That's where most of the people are.
I'm aware of the statistics, but it's like I'm saying, there is a trade-off there, whether you want to increase the number of deaths for heat, decrease.
Fine, but it is a failure of the IPCC not to have included, and it's just a few words, so you don't need a lot of space, the fact that the warming climate has decreased cold-related deaths more than it has increased heat-related deaths.
Okay. So in terms of the book, again, you also have used, of course, this term settled, unsettled, and it kind of evoke a bit the comparison of uncertainty, the term that has been widely used also by the fossil fuel industry since the 90s. So there seems to be a parallel, one might say, but I don't know whether that is intended or not. So what was your intention with the use of unsettled?
So I like to say that the title is really a triple entendre, 3 meanings. One refers to the state of the science, and we have talked about what the certainties and uncertainties are. The second, it refers to how I felt as I started to dig behind the summaries into the data, into the research literature, and discover significant misrepresentation in the media and in the IPCC summaries. And it also refers, the third meaning, to what are we going to do about all of this? And that is this issue of balancing developmental needs, energy needs, against wanting to reduce human influences. Whether the fossil fuel industry promoted the notion of uncertainty or not, I don't know, but the uncertainty is what it is, and I've tried to reproduce that. I've gotten, and many other people have gotten, beaten up for pointing out this true state of the science or the techno-economic realities. But I think we need to do that in order to have a reasonable discussion at the political level about what do we do about this.
And we discussed a lot of the possibilities and actions that governments could take. But in terms, again, on the science aspect, I don't think anybody in the scientific community, the IPCC and related work would question the fact that the science is not settled in terms of all the uncertainties we discussed for projections and so on. We just need to agree on what is settled. I mean, something is settled. The fact that CO2 is increasing, that is driving temperature. Many other things are not settled, and that's why, for example, climate research is continuing. That's why, for example, IPCC is still there. If the science was settled, they would dismantle probably IPCC.
I think not. I think IPCC would continue because it is an important tool for the politicians to point to. The problem I have with the IPCC, again, the reports themselves are actually pretty good, I think. It's when you get to the summaries, the choice of adjectives and adverbs and so on it's manifestly a document meant to persuade rather than to inform. And I think that's where scientists cross a line that they shouldn't cross.
I agree with you on this, although, as you know, the IPCC report has to be negotiated and agreed amongst so many countries, so many people. But ultimately, IPCC is a collection of the science that is available now. The people interested, they can always go and refer to the underlying papers. And so what the only thing they do is to collect all the knowledge we have up to this stage. And ultimately is the governments or other actors, IPCC is there to inform and to provide some background.
Right. And all I'm asking is that they do it accurately and faithfully. And as I say, the detailed reports are pretty good, but by the time you get to the summaries, which is all any non-scientist would read, it gets spun.
Certainly that can be improved. And like we said, so we agree on this. And just a final point, it would be just a call for collaboration, given all your work and your interest and really your sharp intellect in addressing these issues. You said that you're already working on some aspects of climate, that you've been working on that. What are your plans? Perhaps also joining forces with the scientists that are working at IPCC to try to improve the aspects that you said. But in the spirit... I'm happy to engage with anybody in any forum in ways that I would believe are productive. Let me tell you one thing I'm working on now, which is a research project. If you look at and it's got to do with energy rather than climate, but if you look at the energy needs of the poorest countries, or the energy demand from the poorest countries, let's say less than $10,000 a year per capita, the energy use increases almost linearly and universally among all countries. And the slope of that energy use is about 4 megajoules per dollar of GDP. And the research question that jumps out at me as a physicist is, why is it 4 megajoules per dollar? Why isn't it 40 megajoules or 0.4? What sets that scale? And so I'm digging into the data over the last 40 years to see if I can understand what that constant of society is, what determines it. And because that's an important determinant of energy demand over the next 30 years. Excellent. So that's a good way to, I guess, conclude. So I would like to thank you again for your time, for the discussion. I think we covered so many aspects, and I look forward to continue the conversation if there is a possibility through climate, your work that you're doing, and maybe also doing some work together.
That would be wonderful. I'd look forward to that.
Thank you very much, Steve. To reflect on the interview, while Professor Steve Koonin acknowledges that human activity is contributing to global warming through carbon emissions, he questions the extent of its impact. What emerged from our conversation is that the real debate often revolves around the perception of risk. While the certainties and uncertainties of climate change impacts are acknowledged, this must be weighed against the world's growing need for reliable and affordable energy, the nature of energy systems, and the cost-effectiveness of proposed solutions. But should we take more time to plan alternative energy systems, perhaps waiting for innovations to avoid premature investments? Or instead, act now to mitigate what the majority of scientists believe could be an irreversible and dangerous path towards significant climate change? This question of risk and urgency will be a recurring theme in our podcast. Let's communicate. And as I mentioned during the interview, I have great respect for Professor Steve Koonin. Coming from a different but related field of science, he has dedicated significant time and effort to understanding the complexities of climate science. However, this does not mean we agree on all points. In fact, I'd say we tacitly agreed to disagree on many issues. Nonetheless, we hope to continue to communicate. If you enjoyed this episode, I encourage you to explore our other interviews and subscribe to our channel to receive notifications about future episodes, which we plan to release weekly.